Okay, here we go. This is number 7.10 off of homework assignment 4. Let's get to it. So we have some line inside of triangle ABC, and then we have some point on line L. So let's just go ahead and say D is going to be an element of L. And then also, what we're going to do is we're going to say D is an element of the interior of triangle ABC. Now, what this means is we know triangles are the union of three segments of AB, BC, and AC. So we have, if you notice, we also have angles, all right? So we have angle BAC. So D has to be on the interior of BAC. Similarly, it has to be on the interior of angle B, and D has to be on the interior of angle C. All right, and that is going to be important later. So what I'm going to do is I'm just going to go ahead and write that down. We know then D is going to go ahead and be on the interior of, we have triangle, we'll say angle BAC union the interior of angle, how about ABC? Angle ABC union the interior of, the last one we'll say BCA, angle BCA. That looks bad. I need to fix that. Okay, it's on the interior angle BCA. Now, that will become important later on. Let's see here. Next thing we can say is, let's just go ahead and say without loss of generality, let's let ray AD exist. Let ray AD exist. Okay, so what we're going to have is, we know AD, ray AD, so ray AD intersect with BC. We know this is non-empty. Okay, and we know this is non-empty by the crossbar theorem, by crossbar. Okay, now we know ray AD exists, AD intersect B is non-empty by crossbar. So let's go ahead and assume that line L contains ray AD. If line L contains ray D, so let's say this, if AD is an element of L, I guess it would be a subset. If AD is a subset, ray AD is a subset of L, then we're done. Then we are finished. Okay, but it can't be that easy. So let's go ahead and assume that L does not contain AD. So assume, we'll do this in a different color. So assume L, okay, assume L does not contain AD. Okay, now we have to think about this. So if L does not contain AD, we have two things that are going to happen. So we know by I2, by the second incidence axiom, by I2, we know there exists a point P. Okay, there exists a point P such that L equals, we're going to say D.
The 6 p.m. activity bus will be leaving shortly, so please make your way to the common. Thank you.
Sorry about that. We had an announcement at school. So by I2, there exists a P such that L equals DP. Now, what's going to happen here is we're going to have two cases. So case one. Okay, so we'll say case one. Okay, let's let P not be on the interior of triangle ABC. Okay, so if we just think about that, if P is not on the inside of triangle BAC, so maybe P is right here. Okay, so without loss of generality, we know without loss of generality, we know that point D and point P are going to be on opposite sides, of segment BC. Okay, and that's useful. All right, now, since they're on opposite sides of BC, of segment BC, therefore, we can use the plane separation theorem. By the plane separation theorem, okay, by the plane separation theorem, we know we must have that line DP or line L. Remember, DP we said was L. DP intersect BC. This cannot be empty. Okay, therefore, line L meets triangle ABC on side BC. Okay, so that's case one. Now, case two, we'll say case II. Let's go ahead and let P also be on the interior of triangle ABC. Okay, so both point D and point P are going to be on the inside of ABC. Now, what's going to happen from this? We're going to have two cases again. So by the plane separation theorem, I'm going to go ahead and abbreviate this. By the plane separation theorem, two things can happen. So let's consider possibility A. Okay, let's let A, B, and C, A, B, and C all be on the same side. Let's let A, B, and C all be on the same side. On the same side of L. Okay. So if A, B, and C are all on the same side of L, what this means is AB, right, so the union of AB, BC with the union of AB. Okay, the union of AB, BC, and AB. If we look at all of those unions and we take the intersection of those unions with L, what we're going to have is that AB, BC, and AB, the union of the intersection of the unions is empty. Okay, and what this means is that DP is not on the interior of ABC. So this implies L is not in the interior of triangle ABC. Okay, this is a contradiction because by assumption, D and P are on the interior of the triangle. Okay, so that was case A. Now case B. Case A said all 3 points were on the same side of L. What we're going to do now is we're going to say without loss of generality, let's assume that two of them are on opposite sides. Okay, two are on the same side, one is on another side. So let's go ahead and say without loss of generality, I don't know why it switched colors on me. Let A and B be on different sides. Be on opposite sides. I'm going to abbreviate this, opposite sides of L. Okay, so what this means is that if A and B are on opposite sides of L, then by plane separation, again, by the plane separation theorem, we know L intersect AB cannot be empty. It cannot be empty. Therefore, line L must meet one of the sides of triangle ABC. In this case, it's AB. Now I put without loss of generality because I could have made this argument for points A and C, points B and C, whatever. It would have worked for either one of them. So it's the same argument for all three of them. So to kind of recap, what we started with is we had by crossbar, ray AD meets line or segment BC. So if L contained ray AD, then we're done. If L did not contain ray AD, that brought up two cases. Either the second point on line L was on the exterior of the triangle, and if point P was on the exterior where point D was on the interior, plane separation forced an intersection between one of the sides of the triangle. That was case one. Case two was both P and D were on the inside of the triangle. Okay, and then with their both being on the inside of the triangle, that brought up two cases. So case A said triangle A, B, and C, so triangle A, B, C, were all on the same side of line L. Okay, and if they're on the same side of L, that means there's no way point D and point P or point D could possibly be in the interior, which violates our assumption. So there's no way, there's no possibility for A to even exist. Now point B said at least one of those sides of the triangle was on an opposite side. And by the plane separation, if they're on opposite sides, the lines must meet at some point. All right, so covering all of those cases, we have no matter what, that if there is a line inside of triangle ABC that contains point D, then line L must meet triangle ABC at one of the three sides.